Hello friends. On July 26 and 27, 2026, operators at a small water treatment plant in Bram, Minnesota, walked in to find their pumps had stopped. No warning, no explanation, just silence where machinery should have been running. Within hours, more than 30 community water utilities across Minnesota were hit in the same coordinated attack. Cities like Plymouth and Maple Plain scrambled to switch to manual operations. Maple Plain declared a local state of emergency. This was not a movie plot. This was a real cyber attack on the systems that keep tap water flowing to real people, confirmed by Minnesota IT Services and investigated by the FBI and CISA. So how does a water plant get hacked in the first place? To answer that, we need to understand what is actually inside one. Alright, to understand this attack, you need to know about two very different kinds of technology that share the same building. The first is IT, which stands for information technology. Think servers, laptops, databases, email. IT handles data, and if it gets hacked, information gets stolen. Now meet OT, operational technology. OT is the part that physically controls the real world. In a water plant, OT includes PLCs, programmable logic controllers, small computers that open valves and run pumps. It includes HMIs, human-machine interfaces, the touchscreens operators use to monitor everything. And it includes SCADA, supervisory control and data acquisition, the software that ties it all together. If OT fails, the water stops, chemicals get dosed wrong, or pipes can burst. Those consequences are physical, not just digital. And engineers built a layered defense to protect OT from attackers, called the Purdue Model. Now look at this. Engineers built a framework called the Purdue Model to keep those OT systems safe. Think of it like a building with multiple locked floors. Level 0 is the basement, the physical devices themselves, sensors and pumps and valves. Level 1 is where PLCs sit, the controllers we just talked about. Level 2 is the SCADA and HMI layer, where operators watch everything. Level 3 is the operations network. Then comes a critical firewall boundary called a DMZ, a demilitarized zone, a hard wall separating OT from IT. Above it, levels 4 and 5 are regular business IT systems. Every boundary is designed to stop an attacker from tunneling downward to the physical layer. Here's the problem, though. Many small utilities skip the boundaries entirely, leaving their PLCs wide open to the internet. So why do so many PLCs end up reachable from the open internet? Small utilities often have no full-time IT staff. To let an engineer check on pumps from home, they plug a cheap cellular modem into the PLC and call it done. That modem is a direct path from the internet straight into level 1, skipping every Purdue boundary we just talked about. As of April 2026, Census found 3,891 internet-exposed Rockwell Automation hosts in the United States alone. And here's the scary part. Even if you find one, there is a flaw called CVE 202.122.681 in Rockwell Logic's controllers that has no patch. The flaw is architectural, meaning it is baked into every single device. No update can fix it. Now let me show you who is behind this and how their attacks got worse over time. CyberaAttack is an Iranian state-directed hacking group linked to Iran's IRGC Cyber-Electronic Command, the military unit that runs the country's offensive cyber operations. In 2023, they used the simplest trick possible: factory default passwords that utilities never change. Think of it like a front door left unlocked. By 2024, they leveled up with a custom malware called IOCONTROL. It hid its command signals inside normal-looking Internet of Things traffic, so network monitors would not flag it. Then in 2026, they added CVE 202.122.681, the unpatchable Rockwell flaw. Using it, an attacker can pretend to be a legitimate engineering workstation and rewrite what the PLC does entirely. That is the playbook behind the Minnesota campaign. So how do you actually stop this? You enforce every boundary the Purdue model already describes. First, remove any direct path between a PLC and the internet. No cellular modem plugged straight into level 1. That alone would have closed the door for most of the Minnesota attack. Second, put a real firewall DMZ between your operations network and your business IT network. Third, any remote access must go through a gateway that requires multi-factor authentication. That means a second proof of identity beyond just a password, such as a code sent to your phone. Fourth, Watch the PLC project files. If a file changes and no engineer authorized it, that is your alarm. Each layer blocks one stage of the attack chain, and that is the pattern we need to zoom out and understand. And that brings us to the bigger pattern. The Minnesota attack, where more than 30 water utilities were hit over 2 days in late July 2026, was not a fluke. It worked because of 3 structural problems sitting right out in the open. First, PLCs directly reachable from the internet, with no barrier in between. Second, a core architectural flaw in Rockwell controllers that no software update can ever fix. Third, flat networks where IT and OT systems share the same space, so one breach spreads everywhere. The investigation is still active as of July 29, 2026. But the lesson is already clear. When you cannot patch your way out of a problem, your only real defense is distance. Segmentation means an attacker who gets through one door still cannot reach the controls. Thanks for watching, and we will see you in the next one.